acid-base titration, dealing with a weak base and a strong acid. As we can see in this graph over here, we have base within the solution. It has a quite high pH. As soon as we start adding some of the acids going towards the right, as we can see, the pH starts to go down. When we hit that buffer region, the concentration of the acid is only half the concentration of the base, which makes sense because the base is extremely weak and the acid is extremely strong. So we only need half the amount of acid concentration in order to hit this buffer region. Remember, the buffer region is where there is equal amounts of weak base and its conjugate acid. Now, why is this equivalence point all the way down here below a pH of 7? Okay, it's a lot less than the 7 pH. Well, let's have an illustration here with these two examples. Well, we have NH3 over here, which is a base. It's going to accept the proton, so this becomes NH4 plus. And then we have this OH minus still floating around, so we're going to be adding that with our HCl within the beaker. And then, of course, we're going to have some neutralization. How do we know that this is neutralized? Well, water is obviously neutral, and then this Cl minus is going to be a weak base. Why? Because it is the conjugate base of this acid over here. And we know HCl is a very, very strong acid, right? So we have here HCl is a very strong acid, which means chloride ion is going to be a weak base. Now, what about the cation, ammonium? Well, this ammonium, we're going to be looking at this one right now. We've already dealt with the OH minus. We're dealing with this one now. So this NH4 plus, when we dilute it and let it dissociate with the water, we end up getting this and this, right? Because, of course, this is going to be donating it towards the H2O because this is already positively charged. It doesn't want another proton. So we get NH3 and H3O. Well, H3O is hydronium, which is the definition of an acid. So we have an increase of this in the product. This causes an increase of the pH to go up, and hence why the equivalence point tends to lower or tends to drop. We have our CV and Ns over here, and then we can easily find our moles. We know that this mole here also needs to be 6 10 to the negative 3 because we have the equivalence point over here, right? Which means we have C, we have N, we don't know what our V is. You can just use C is equal to N over V to isolate for the V. We get 0.03. We create our little ice table. This is, again, all in moles over here. We're going to combine our two beakers of this liter together. So this is liters on the bottom, so we have our concentration. Now, are we going to be using the acid route or the base route for these equations? Well, we're titrating with an acid, right? We're titrating it with our HBr, so let's use the acid route. So in this acid route, we put them all into this little ice table with that concentration that we had earlier over here. We use our K is equal to our products on the top and our reactants on the bottom. Again, products on the top, reactants on the bottom. We put them all into a quadratic formula equation over here so that we can isolate for our X, our concentration. We put that concentration within our pH formula because we're trying to find the pH. So we got 2.31 times 10 to the negative 5. Put that in there, we get a pH of 4.64. Try these two questions on your own. I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question.